Okay, so now we get Cramer's rule. And again, this is another way to solve systems. I'm going to illustrate it with an example where we have two equations and two unknowns because it's pretty quick and simple to solve. And then I'll have you see if you can repeat the process on a system that includes three equations and three unknowns. But the principle is easily expanded. So let's take x1 plus 3x2 equals 4, x1 minus x2 equals 0. So this is going to be our system. So initially we start out by designating the coefficient matrix that comes from the left-hand side of the equation here as A. So we'll take that to be the matrix 1, 1, 3, negative 1. And then we make a new matrix called B sub 1. And what we do is we replace the column in the x position, or x1 position here, with the solutions on the other side of the equation. So in this case, that means we put in 4, 0 in the place of the x1 column, and then keep the x2 column the same, 3, negative 1. And we make another matrix B sub 2 that does the same thing, but with the x sub 2 column. So now again, we use these solutions here, 4, 0, and replace the second column in the matrix A to make another new matrix. So this is going to be the matrix 1, 1, 4, 0. And then we can find the solutions from our system here by finding the determinants and taking some ratios. So x sub 1 is what we get when we take the determinant of B sub 1 divided by the determinant of A. And x sub 2 is going to be the determinant of B sub 2 divided by the determinant of A. And those are pretty quick to compute in this particular instance. The determinant of A is going to be negative 4. And the determinant of B1 is also negative 4. And B sub 2 is also negative 4. So in this case, the solutions look like 1 and 1. And we can go back and verify that just to make sure that we've got it right. If we plug in 1, 1 into the top equation, we do in fact get 4. If we plug in 1, 1 into the second equation, we do see that we get 0. So this is in fact the solution to the system. So this is generally how Cramer's rule works. For a 3 by 3, it works the same. So for a 3 by 3 system, in other words, 3 equations and 3 unknowns, it works pretty much the same. You just have to expand the concept so we have more determinants to work with. So let's say we have a system that looks like x1 plus x2 plus x3 equals 2, and x1 plus 2x2 plus x3 equals 2, and x1 plus 3x2 minus x3 equals negative 4. So I'll set up these individual matrices for you, and then you can compute the determinants to get the solution. So A is going to be the coefficient matrix, 1, 2, 3, and 1, 1, negative 1. And then we get the matrix B1 we'll take. And again, we get that by replacing the x1 column with our solutions 2, 2, and negative 4. So we'll plug that in, and I'll do a different color here so we remember these are coming from a different place. But the rest of the matrix stays the same. The matrix B2 is going to come when we replace the x2 column with the solutions. So it's going to look like 1, 1, 1, 2, 2, negative 4, and 1, 1, negative 1. And then we get this last matrix, B3, which is going to be equal to what we get when we replace the third column in the matrix A again with our solutions. So 1, 1, 1, 1, 2, 3, and 2, 2, negative 4. Then we can find the solutions x1, x2, x3 in the same way we did before. X1 is going to be the determinant of B1 divided by the determinant of A. X2 is going to be equal to the determinant of B2 divided by the determinant of A. And X3 then is the determinant of B3 divided by the determinant of A. And you'll see different authors use some different notation. I'm just trying to stay consistent with what this particular author has chosen for his notation on how to set up Cramer's rule. But do be aware that if you're watching other videos or you're looking at other sources, that you might see this written out in a slightly different version. In the end, it all works out and means the same thing. This is just what our author chose to do in this case. So I'll leave it to you to go ahead and finish this off and compute the determinants and verify your solution.